Hey guys, welcome to Learn Today IGCSE. In this video, we'll go through all Chapter 3 Waves questions from the 2024 IGCSE examinations, including February, March, May, June, and October, November, covering all three variants. Let's get started. Question 5, Part A. Table 5.1 shows applications of regions of electromagnetic spectrum. Complete the second column of the table with the region of the electromagnetic spectrum used for each application. Choose from the regions in the list. Okay, hereby you are given the application in this column and you have to fill it up with the region, and the options are all given over here. They should be pretty easy as long as you have memorized the region and its application accordingly. If you haven't, you can just take a screenshot of this and make sure to memorize them. And also remember the order of the spectrum from the lowest frequency to the highest frequency. Next, Part 2. State the approximate speed of radio waves in air. All electromagnetic wave has the same speed as the speed of light in air, which is 3 times 10 to the power of 8 meters per second. Next, question B. Figure 5.1 shows successive crests of a wave after a plane wave has passed through a gap. So the wave has passed through the gap, and this is what we observe. On Figure 5.1, draw 3 successive crests before the wave reaches the gap. Okay, when waves go through a gap, it will be diffracted. You must know the factors that affect the magnitude of diffraction. The question shows you the case whereby the diffracted wave looks like this. The waves are curved as a C-shaped, which means that the gap is equal to the wavelength of the wave before it went through the gap. So we are going to draw 3 lines which has the same wavelength as the gap. So this is what it should look like. Part 2, Figure 5.2 shows a much wider gap. A plane wave of the same wavelength as in B Part 1 is incident on the gap from the left side of the barrier, meaning that we're going to take the same wavelength of the waves from Part 1 and put it on the left here. On Figure 5.2, draw 3 successive crests of the wave after the wavelength has passed through the gap. As you can see here, the difference is that the gap here is much larger compared to the wavelength. When the gap is bigger than the wavelength, there will be a lesser diffraction. So you're just going to curve a little bit at the end of your waves, like this. And make sure that the wavelength is the same as before. Next, question 6. Figure 6.1 shows a full-scale diagram of an object O and its image I, produced by a converging lens. We have 2 types of lens that you will learn in your syllabus. This is a converging lens, known as a convex lens, and another one is a diverging lens, which is known as concave lens. Question Part A. On Figure 6.1, draw a single ray to locate the position of the center of the converging lens, and a line to represent the position of the lens and label the line as L. This question here is a little bit different from every other past year questions. Usually they will be giving you a lens and then they will ask you to locate the image. Or they give you an image with the lens and they ask you to locate the object. But right now, as you can see, it's a little bit different. You have the object and image and you are asked to locate the lens. To do this, the rule is the same. When locating an image, you have to always draw a straight line from the tip to the center of the lens. And the second line always goes through the center of the lens, elongate it until it reaches the tip of the image. So we will use our second line here to determine the center of the lens. So we can draw a straight line from the tip of the object to the tip of the image. The point of when the line intercepts with the principal axis is the center of your lens. And we should draw a line to represent the position of this lens. I'll just draw a simple line like this and label it as L. Okay. Next question is asking us to determine the focal length of the lens by drawing another ray on Figure 6.1. Focal length is from the center of the lens to the focal point. To determine the focal length, we first must find the focal point. Now that we know the center of our lens, we can draw a straight line until the center, and then from that point onwards, we can elongate and touch the tip of the image. And the line that intercepts the principal axis is our focal point. So we draw a straight line from the tip of the object to the center of the lens. And then from there, we will elongate until we arrive to the tip of the image. This point where it intercepts with the principal axis will be your focal point, and let's label it as f. So the length between the center of the lens to the focal point is my focal length. From here onwards, I can just use a ruler and measure the distance. I get roughly 2.1 as the distance. So the length here is 2.1, and the unit will be centimeters. Next, question C. The object is moved 2 centimeters closer to the lens. State 2 changes to the characteristics of the image. Okay, the object right now is placed at 2.9 centimeter. If it was moved 2 centimeters closer, the object's new position would be over here. So let's see what happens to the image of the object. The first line would be to the center of the lens, and then it will go through the focal point like this. And the second line would be from the tip of the object towards the center of the lens, and we will just extend the line. As you can see, these two lines do not intercept over here. But we can backtrack this line and we will see that the image falls somewhere behind over here. So this means that the image is virtual and it is upright. The image previously was real and inverted. That's how different it would be. If you're finding this useful, check out my website where I've compiled IGCSE exam questions by topic from 2020 to 2024. The link is provided in the description box below, or you can just click on learntodayigcse.com. On the website, you will see all the revision courses and click on physics topical questions, and you get to see a preview down here. Once you're ready, add it to your cart and proceed to check out. Just enter your name for billing purposes. Don't worry about the address, you can just use the sample one provided in the video. Since this is a PDF ebook, nothing will be shipped to you. Once the payment is complete, you'll be able to download your copy immediately. The next question is from May-June Paper 4-1. The lens in the magnifying glass is a converging lens. Remember, we have two types of lens. This is a converging lens and this is a diverging lens, which can also be known as concave, and this would be convex. Question A. Figure 4.1 shows the lens of the magnifying glass. Its two focal points f1 and f2 and its principal axis. Question part 1. State what is meant by focal point. If you look into your course syllabus, you would see that you are required to know the terms focal length, principal axis, and principal focus. However, the definition is not given to you. So focal point is the point where parallel light rays passing through a lens intersect the principal axis. And additionally, I have also provided you with the definition of principal axis and the definition of focal length. So be sure to memorize them. Question part 2. A student using the magnifying glass sees a magnified image of an object. On figure 4.1, mark a point X on the principal axis for a possible position of the object and a point E for a possible position of the student's eye. These are the 4 possible positions where the objects could be. And for the case of a magnifying glass, the object is placed between the focal point and the center of the lens. And this is where your eye position is. The image of a magnifying glass is located behind the lens and the image is usually larger. And this is your eye position. So to get a magnified image, a possible position for the object is between the focal point and the center of the lens. And the position of the eye is somewhere at the bottom here. This is point X and this is point E. Next, part 3, underline 2 words in the list that describes the image produced in A part 2. So as described previously, the image will form behind the lens and it will be magnified. The first line should go from the tip to the center of the lens. The second line goes through from the center of the lens and passes through F, which is the focal point. And the third line will go through the center of the lens. However, in this case, you can see that these two lines do not intercept with each other. So you need to backtrack the line and you will see that the image falls behind the lens like this. And whatever that is behind the lens, we call it as virtual. If you have a hard time remembering it, you can just draw the letter R over here. So this means that whatever which is on the right side would be real. And since the image is bigger than the object, this would be described as magnified and the object is upright. If it's like this, then it's inverted. So it's upright and virtual. Question B. The refractive index of the glass used to make the lens is 1.5. The speed of light in air is 3 times 10 to the power of 8 meters per second. Calculate the speed of light in glass. The formula related to this is n equals to c over e. Rearranging this formula, we would get c over n. And just put this value in your calculator and you will get 2.0 times 10 to the power of 8. Since we are calculating speed, the unit of speed is meters per second. Next, part 2. State what happens to the wavelength of light as it passes into the lens. So air to lens, the wave is entering a different medium. Therefore, the speed will change, which causes the wave to change direction. Now, if the wave speeds up, the wavelength will increase. And if the wave slows down, then the wavelength decreases. In this case, as you can see, the speed decreases. So if the speed decreases, then the wavelength decreases. And here I have attached the summary for you. Next question, part C. Converging lenses are usually used in classes to correct one problem with vision. State the name of the problem and explain how a converging lens is used to correct it. You may draw a diagram. And if an image falls behind the retina, then the problem that you're facing would be long-sightedness. So to correct this, we have to bring our image to fall on the retina. To do this, we are going to use a converging lens, as converging lens can help to bring the image forwards towards the retina. Next, question 5, part A. Describe how a longitudinal wave differs from a transverse wave. So you can check this on your course specification. It says that a longitudinal wave, the direction of vibration is parallel to the direction of propagation. Whereas for transverse wave, the direction of vibration is at right angles to the direction of propagation. Next, question B. Figure 5.1 represents a seismic wave produced by an earthquake. You should know that seismic S waves can be modeled as transverse wave, whereas seismic P wave can be modeled as longitudinal. And this image here portrays a longitudinal wave, which is a seismic P wave. Question part 1. State whether seismic wave is a P wave or an S wave. Justify your choice. So you can just say it's a seismic P wave as it is a longitudinal wave. Next, part 2. The wave represented in 5.1 has a wavelength of 1.2 times 10 to the power of 4 meters. Calculate the actual distance between point J and point K. We are given with the length of one complete wavelength, which would be from the center of one compression to the center of the next compression. So here is one complete wavelength, and the next complete wavelength would be to the next center of compression. K is located at the center of a wavelength. So this means that between J to K, we've got 1.5 wavelength. So we can just do the distance of one wavelength multiplied by 1.5, giving us 1.8 times 10 to the power of 4, and the unit here is meter. Next, question part 3. The wave in part 2 travels from the ground at a speed of 4,600 meters per second. As the wave passes a certain point, the ground completes 5 oscillations. Calculate the time that it takes for the wave to pass. Show your working. Okay, so we are looking to find the time, and we have velocity and the number of oscillations. Now, to find time, we can use 1 over frequency. However, we are not given with the frequency. So to find the frequency, we can use our formula of velocity equals to frequency times wavelength. So the frequency is 23 over 60, and the time taken would be 1 over the frequency, which is 2.61. Now this is the frequency for one complete cycle, and we've got 5 oscillations. So we'll just multiply our answer by 5, giving us 13.04 seconds. In two significant figures, that would be 13 seconds. Next, question 5. Figure 5.1 shows a ray of yellow light incident on a glass prism ABC. Okay, question A. Explain why the ray does not change direction when it enters the prism at face AB. So when the light enters, it doesn't bend this way or even get reflected. Instead, it travels all the way in a straight line. The reason is because when a ray of light strikes the boundary at a 90-degree angle, it will continue to travel in a straight line without changing any direction. Next, question B. The critical angle for the glass is 42 degrees. Calculate the refractive index of the glass. Some of the formulas that you have to remember from your chapter of light is that the value of refractive index is equal to 1 over sine C, C being the critical angle. So the formula related to critical angle and refractive index is n equals to 1 over sine c, and the value of refractive index would be 1.5. Next question, part 2, on figure 5.1. Continue the path of light through the prism and after it leaves the prism. Okay, in order to continue the path of the ray of light, we're going to need a protractor. So the first thing we're going to find is the incidence angle. Only then we can identify whether the ray of light would reflect, travel through the prism, or get refracted into the air. So the angle that I have obtained is somewhere around 58 degrees. Now we're going to have to find out whether it reflects, goes through the prism, or gets refracted out into the air. And to identify that, we first must know these 3 rules. If the incidence angle is bigger than the critical angle, the ray would be reflected here. If the incidence angle is equal to the critical angle, the ray would continue to run along the boundary. And if the incidence angle is smaller than the critical angle, then the ray of light will be refracted out of the glass. So let's look at the critical angle. The critical angle here is 42 degrees. So the incidence ray is larger than the critical angle. So what's going to happen here is that the ray is going to be reflected. So remember that when the ray is reflected, it will reflect at the same angle of the incidence. So that would be 58 degrees as well, which is actually going to end up being a straight line. And now that it enters the face of AC at a 90-degree angle, as we discussed previously, so the ray of light now will continue to travel in a straight line. So this is what your final ray of diagram should look like. Next question, part C. Internet data can be transferred using infrared waves in an optical fiber. State 2 advantages of using optical fibers to transmit data. Since this question is theoretical, we can easily get the answer from the course specification. Under chapter 3, you will see that the advantages of using optical fibers, which is due to its transparency to visible light and that they can carry high rates of data. So you can mention those 2 in your answer space. Next, question 6. A sound wave travels through the air. Figure 6.1 shows a pressure time graph for the air at one place. Alright, part 1. Label one point C to indicate a compression and one point R to indicate a rarefaction. Now remember that compression is a region of higher pressure. So we are going to label point C over here, which is the highest point of the wave, and rarefaction is the region of a lower pressure. So we are going to label R here at the lowest point of the wave. Next, part 2. Explain why this graph cannot be useful to find the wavelength of the sound wave. To find the wavelength of a sound wave, we are going to need the displacement, and we have not been given with the displacement in this graph, so we can't use this graph to find the wavelength. Next, part 3, the sound becomes louder and lower pitch. See what happens to the amplitude and the frequency. Amplitude is the height of the wave. The bigger the height of the wave, the louder the sound would be. So if the sound becomes louder, it means that the amplitude increases. And the frequency of the sound relies on how close the wavelengths are to each other. The closer they are, the higher the pitch. And the further away they are from each other, the lower the pitch. So for lower pitch, the wavelengths will be further away from each other. Means that the frequency right now decreases. A higher frequency means that a higher pitch, and the wavelength would be more closer to each other. Next, question B. A sound frequency 13 kHz is transmitted through water. The speed of sound in water is 1500 meters per second, and we are asked to calculate the wavelength. The formula related to wavelength, speed and frequency is V equals to frequency times lambda. Lambda here is the wavelength which we are looking for. So rearranging this formula, we would get velocity over frequency. Velocity given is 1500 meters per second. There is no need for us to do any unit conversion because meters per second is the standard SI unit. However, the frequency given here is in kilohertz and we have to convert this to hertz. Kilo means times 10 to the power of 3. So it will be 13 times 10 to the power of 3 hertz. And the wavelength that we will obtain is 0.12. And the unit here would be meters. Next, question part C. State the approximate speed of sound in air. The speed of sound in air is approximately 330 to 350 meters per second. So you can write any value between 330 to 350, including your unit. Next, question 6. Figure 6.1 shows a thin converging lens used to produce a magnified image of an object AB. Question A. Explain the meaning of the terms principal focus and focal length. So we have gone through this in the last past paper, the definition of principal axis and focal length. Next, question B. In figure 6.1, draw the magnified image of AB and show all your working. Now, when you are given for lens drawing, remember the first line should be from the tip of your object to the center of your lens, and the line has to be parallel to your principal axis. And the second line is from where you stop, which is at the center of the lens, passing through your focal point, like this. And for the third point, it goes from where you begin, which is the center of the object, going through the center of the lens and just extend it. Make sure it passes through the center of your lens. So usually these two lines will intercept with each other at a particular point. However, you can see that they are not intercepting. So now you have to extend your line to the back of the lens like this. And the point where it intercepts is where your image is formed. Next, question 8. Figure 8.1 shows images produced during two different medical scanning procedures. You've got an ultrasound scan of a fetus and an X-ray scan of a hen. Question A, Part 1. Define ultrasound. You can get the definition of ultrasound in your course syllabus. It is a sound with a frequency higher than 20,000 Hz. Next question, part 2. State how the speed of sound in liquid compares to the speed of sound in air. Now, speed of sound, so it goes from solid to liquid and the slowest to air. So comparing liquid to air, the speed of sound travels faster in liquid. Part 3. X-rays are part of the electromagnetic spectrum. State the speed of X-rays in a vacuum. All electromagnetic spectrum in a vacuum will travel at the same speed of light, which is 3 times 10 to the power of 8 meters per second. Make sure you remember this. Next, question part B. Describe 3 similarities or differences between the use of ultrasound and X-rays in medical scanning procedures. So these are some of the similarities and differences that you can go through yourself. Next, question 5. A loudspeaker produces a sound wave in air. The distance between the center of a compression and the center of a neighboring rarefaction is 0.1 meters. Sound wave is a longitudinal wave, and this is what it looks like. This part with the lines closer to each other is called a compression, and the lines which are further from each other is called rarefaction. A complete wavelength would be that if you start at one point of compression, you end at the next cycle of compression. If you start at the center of a rarefaction, it has to go all the way up to the next center of rarefaction. That's what makes a complete wavelength. In this question, it's given us that the center of the compression to the center of the neighboring rarefaction, this is a rarefaction and this is the center of the neighbor, is 0.1 meters. So the wavelength would actually be from here to here. So since this is only half, the other half would also be 0.1 meters. So the wavelength here is 0.2 meters. Next question, part B. State a typical value for the speed of sound in air. You must know the speed of sound in air and the speed of light in vacuum. The speed of sound in air is approximately 330 to 350 meters per second. Since they just want one value, you can give any value from this range. Question C, part 1. Calculate the frequency of the sound from the loudspeaker. Okay, a formula related to the frequency of the sound, speed of the sound, and the wavelength is the formula speed equals to frequency times wavelength. Rearranging the frequency, we would get velocity, which is the speed of sound, over the wavelength, giving you a frequency of 1650 Hz. If you're using a speed of sound which is 350, you would get a frequency of 1750 Hz. So any value from here to here would be an acceptable answer. So changing this to two significant figures, 1700 Hz. Next question, part 2. Explain whether the sound from the loudspeaker is audible to a human with normal hearing. Now, the approximate range of frequencies audible to humans are from 20 Hz to 20,000 Hz. Please remember this range. Since the frequency here is within 20 to 20,000 Hz, yes, you will be able to hear the sound. Next, question D. Another loudspeaker produces a sound of wavelength 0.4 meters. Sound from the loudspeaker reaches a sound-absorbing surface, this one, with a gap of 0.8 meters. Okay, figure 5.1 shows the arrangement. Explain whether it is possible to detect sound from the loudspeaker at either point J, which is here, or at point K, which is here. Okay, now, when the sound wave goes through a gap, the sound wave will diffract. However, the way it diffracts depends on the gap. If the gap is smaller than the wavelength, then the waves tend to diffract more like this. However, if the gap is larger than the wavelength, then there will be less diffraction like this. So in this case, the gap is 0.8 meters, which is larger than the wavelength of only 0.4 meter. So the diffraction of sound here will be very less. Therefore, we can assume that the sound that is being heard at this position J would be very little to no sound, as the diffraction here is going to be very less. However, at point K, the wavelength will travel and there could be more sound. So this is how you can answer to obtain 4 marks. Question 6. A student plays the violin near the doorway to a large room. Figure 6.1 shows a young teacher standing where he can hear the sound but cannot see the student, which is over here. Question A, Part 1. State the wave effect that allows the young teacher to hear the sounds from the violin at the position he is standing in Figure 6.1. Sound wave is a longitudinal wave. As it travels through a gap, the wave will diffract. And that's how it reaches the teacher who is standing in this position. So the effect is diffraction. Part 2. Calculate the frequency of sound with a wavelength of 0.75 meter. The speed of sound in air is 340 meters per second. So the formula related to wavelength, speed of sound and frequency is speed equals to frequency times lambda. Lambda represents the wavelength. So rearranging this formula to calculate frequency would be speed over wavelength. Just make sure that the speed and wavelength are in standard unit, and the frequency in 2 significant figures would be 450. The unit is hertz. Question Part 3. A violin produces sound in the frequency range 200 Hz to 3800 Hz. The width of the open doorway is 0.75 meters. Explain why the young teacher hears the frequency calculated in A Part 1 clearly but finds a frequency of 3500 Hz much harder to hear. The frequency calculated in A Part 2 is 450 Hz, and the one which is much harder to hear is 3500 Hz. Now, a higher frequency means the wavelengths are closer to each other. So if the wavelengths are closer to each other, in comparison with the size of gap which is much larger than the wavelength, it will cause the wavelength to diffract lesser. Therefore, it will be harder to reach this teacher in this position. So the higher the frequency, the smaller the wavelength. The lower the frequency, the wider the wavelength. Remember that if the wavelength is larger or equal to the gap, there will be more diffraction. But if the wavelength is much smaller than the gap, then the diffraction would be much lesser. Next question, Part B. A plane mirror is placed at point X so that the teacher can see the student. On Figure 6.1, draw a light ray from the violin to point X and from point X to the teacher. Draw and label the mirror, and then add an arrow to the ray to show how the teacher sees the student. So we'll place a mirror and label it at point X. The image of the student will travel in a straight line and gets reflected on the mirror to the teacher in a straight line. Remember that for reflection, the angle of incidence is going to be equal to the angle of reflection. You can just write I equals to R. Next, we'll jump into question 8 first, and then I will do question 7 next because this is the same topic as question 6. A fisherman uses high-frequency sound waves to locate fish in the sea. Figure 8.1 shows the sound waves emitted from the boat. State the name of sound waves which have a frequency greater than 20 kHz, which is equivalent to 20,000 Hz. Under the topic 3.4 sound, you must know that ultrasound is a sound with a frequency higher than 20,000 Hz. So this would be ultrasound. Next, question B. High-frequency sound waves travel from the boat through the sea water. The speed of sound in water is 1,500 meters per second and the seabed is 22 meters below the boat. So the sound is traveling at a speed of 1,005 meters per second and the depth is around 22 meters. Okay, we are asked to calculate the time taken for the boat to receive the reflected wave from the seabed after the sound is emitted. So we would like to know how much time is taken for it to reach the bottom of the seabed and then reflects back. So that means it traveled 22 meters downwards and 22 meters upwards. So the total distance would be 22 times 2, which is 44 meters. To calculate time when given speed and distance, we can use the formula of speed equals to distance. And rearranging it, we will get time equals to distance over speed. So the distance is 22 times 2 as it goes down and then get reflected up. And the speed is 1500 meters per second. So the answer is 0.029 seconds. Next question C. Figure 8.2 shows a fish below the boat. Describe and explain how the reflected sound wave received by the boat from the fish differs from the reflected sound received from the seabed. Okay, meaning to say that there are some wave which hits the fish and get reflected back to the boat, and some wave that hits the bottom of the seabed and get reflected to the boat. Since fish are very small, the wave that get reflected back is going to be very little, whereas the seabed is very broad and wide, so they will receive much more reflection after hitting the seabed. So that's how you can differentiate whether it's being reflected by a small object or by the depth of the sea. Next question 4, part A. Figure 4.1 shows a ray of light as it enters the side of a plastic box. The ray of light passes from air into the plastic. So you can see that the ray of light travels in a straight line, but once it hits the boundary, instead of going straight, it bends towards the normal. Question part 1. State how the speed, wavelength, and frequency of the wave in the plastic block compare with the values in the air. When light travels from air into another medium, in this case solid, the speed would decrease. And if the speed decreases, then the wavelength decreases as well. However, the frequency will always remain the same. Here's a summary of how wavelength, speed, and frequency is affected in case of water, where it moves from a deeper region to a shallow region, and the second one in case of light when it travels from air into glass, and the third case of sound traveling from air into water. You can take a screenshot of this and make sure to understand and remember them. Next question part 2. Show that the refractive index of the plastic is 1.4. Okay, so there are 3 formulas to calculate the refractive index. And for this question, we can calculate using the incidence angle and the refracted angle, which will give us a value of 1.4. Next, part 3, calculate the critical angle. So now that we have the refractive index, we can use this formula to calculate our critical angle. So sin C is 1 over 1.4. Rearranging this, we can just put it in our calculator. You will get 45.58 into significant figure would be 46 degrees. Next question, part B. Figure 4.2 shows the same plastic as in part A to make an optical fiber. A ray of light is passing along the fiber. Part 1, carefully continue the ray of light P until it reaches the other end of the fiber. So remember that the ray of light will just get reflected. However, it has to be reflected in a way that the incidence angle is equal to the reflected angle. So this is what it should look like. Next, part 2, state 2 uses for the optical fibers. These are some of the uses for optical fibers. These are all theoretical questions, so make sure you go through your syllabus and memorize them.